Agorni, da Universidade de Udine, na Itália. Ele vai falar sobre Special Interaction and Functional Lotka-Volterra Prey-Predator Systems. A palestra será em inglês, acredito.
Can you hear me? Yes. So I wish to thank the organizer, especially Riccardo, for his work on this conference in honor of our friend Angelo Barone. I got to know him in 1990 here in São Paulo. Then we worked together also with Gaetano a few years later in Italy. Then I was here back second time in Brazil in 1999 when I took this picture coming back from Ubatuba. Nice holiday. So yes, during this my stay here in 1999, we wrote a paper also with Mauro together. So well, but my talk will be about something completely different. Spatial interaction and functional response in Lotka-Volterra prey-predator systems, which is a work we did with a student, graduation student at the University of Udine. I think it is nice enough for a talk because it's entertaining. It's interdisciplinary. It brings together biology, ecology, differential equation, probability, special functions, and computer simulation all together. I won't call it cutting-edge science because we didn't read all the literature on the subject. We only read a very small part of it. So maybe somebody else did something similar or maybe better. But it was fun to do it, and I hope I will share some of the fun with you. The student's name is Elena Bozzetto. So, I think population dynamics starts with Malthus in 1798 with his work, an essay on the principle of population. He wrote it in English, not in mathematics, but his idea can be translated into a differential equation, x prime equal to alpha times x. Very simple equation. Now, what about simulating a population that grows according to this equation? A stochastic simulation, not a deterministic. Deterministic simulation is too easy. So here is an example. I start with the square, with an animal, a bacterium in the middle. And now, at discrete times, I decide whether the bacterium reproduces or not. I mean, reproduces in the sense that it doubles, it becomes two bacteria, with a fixed probability, say alpha, is the probability of reproduction at a given time, discrete time. So, and at the same time, I will move the bacterium around in a Brownian motion way, so it doesn't, I mean, all the bacteria move around. So let's look. Oh, it has reproduced, no more, and more. I can watch a population is 150 going up. There is a plot of the population. You can see that it is growing exponentially. After a while, the simulation goes slowly because there are too many points to keep track of. So, this is a very simple simulation of a population dynamic. Next, in the history of population dynamics, come Verhulst in the mid-1980s, which came up with a so-called logistical equation, which is a more refined version of Malthus' equation, because it contains this term beta x squared with a minus sign, and this term takes into account overpopulation. So this term discourages the growth of the population, and you probably know about this. This is the flow of this equation. There is an equilibrium population that stays stable, and populations that start over it will decrease. Populations that start below will grow and converge pretty fast to the stable population. Now, what is the justification for the term beta x squared? Actually, we gave a look to Verhulst's paper, and we didn't find a clear justification, except that it is easy to calculate. It is mathematically easy. But there is no insight into why x squared and not something else. So there is no theory, microscopic theory, of why it should be x squared. And Verhulst didn't even tell us why he called it a logistical equation. He just says it is logistical, and we don't know why it is logistical anyway. So, but well, we could try a simulation of this, similar to the Malthus equation, but I won't go into it because we don't have yet a theory behind this beta x squared. What we have is some kind of theory behind the Lotka-Volterra equation. So Lotka-Volterra came up with the same equation about at the same time, 1925-26. Lotka a little earlier. But I know more about what Volterra did. He started with this chart here, histogram, which is histogram of the percentage of sharks over all the fishing that came into the harbor at Fiume in northern Adriatic Sea around the time of the World War I. So you can see that before the war, sharks were about 12% of the whole fish. After the war, it came back to 12%. But during the war, you see, it was percentage of sharks was much higher. So somebody saw who compiled these statistics was surprised and asked Volterra to think about it. And he thought about it, and he came up with a nice theory. Well, the explanation why sharks go up during the war is that, well, it's pretty simple. You can say it in words. I mean, trolling nets get all fishes with the same probability. Sharks are doubly hit by fishing because first they get caught, and then also the nets catch the food of the sharks. So they get caught, and the survivors get less food. So they are doubly hit. The other fish, non-sharks, get caught, of course, but then they are helped a little because they find fewer sharks. So when the war starts, there is much less fishing because it's dangerous. So sharks get an advantage, or rather, get back the advantage that they had before humans started fishing. So this is the explanation for the statistics, but Volterra equations tell us much more than this. They're much more interesting. These are the equations. You probably know about them. So X is the prey total number, Y is the predator total number. This is the flow phase space of Lotka-Volterra. You can see all the also the solutions are closed. They go around the equilibrium point. Oh, this is a most symmetrical situation. We can change the parameters. Anyway, for all possible values of the parameters, you get a flow that goes around counterclockwise around the equilibrium point. And this is the flow, I mean, not the flow, but the time series. On the horizontal scale, there is time. On the vertical scale, there is the population. You can see that first, for example, preys go up because there are few preys. Predators get a little food, they go down. But then the preys become more, so predators get up, and there is a nice oscillation, and the predators are a little later, come a similar oscillation, but later. Oh, this is, I think, familiar to most of you. Some examples, I mean, biological examples of oscillations. The most famous one is the Arctic hare, for which we have a time series starting before, I mean, in the mid-1700s. You can see that there are oscillations, and with a nice periodicity. The periodicity is about 10 years. It goes up and down after 10 years, each 10 years. Another example is the lynx, Canadian lynx, for which we have also a time series. You can see also oscillations with the same cycle, I mean same period, 10 years. So we may think that they are linked because they live in the same habitat. If we compare the two, well, it is not very clear. Here, for example, they seem to be synchronized. Here they are, well, synchronized a little. See, in the phase space, this is the phase space map. Well, it is a jumbo, but if we restrict to about 1850 to a few cycles are very nice. Here, these two cycles are, look very much like Lotka-Volterra cycles. They go counterclockwise. Well, but there are other cycles which go the other way, so it's not very clear that this is a Lotka-Volterra situation. It's not very clear, but another population that follows some cycles is the lemmings in the Arctic tundra. For example, this population here in a special spot by Lot Island, probably in Greenland, has a 4-year cycle. And I read the paper saying that probably this Fourier cycle is due to the interaction between the lemming and the stoat, Arminio. Interaction between these two animals may drive the oscillation in that place, because it depends on the places. So, some criticism of Lotka-Volterra equation. There are many criticisms. Volterra knew about them, of course. One criticism is that there is no control for the overpopulation. I mean, the two populations keep check on each other, but there is no intrinsic system to avoid overpopulation. I mean, if you don't have predators, the preys go up exponentially. Another problem with Lotka-Volterra is that, for example, take this simulated population. I mean, the little wolves are the predators, the blue dots are preys. I mean, for example, the probability of this predator eating a prey does not depend on the number of the predators. For example, if I take a lot more predators, a lot more, I mean, with the same prey, the probability of each one eating a prey is the same as before. This is not reasonable. And the same for the preys. The probability of the prey being eaten is independent of the number of the preys. For example, in this situation here, the probability of a prey being eaten is the same irrespective of how many preys there are. Sorry, how many preys there are. So this is not reasonable. Also, the time it takes a predator to eat a prey can be arbitrarily small. I mean, if I put a lynx inside a room with 10 hares, it can eat a hare in, say, 1 minute. If I put 1,000 hares here and one lynx, it will eat a hare in 1 millisecond or something. This is not reasonable. So, classical Lotka-Volterra is not, can be criticized. So, here comes Holling, a Canadian entomologist in the 1960s, came up with the idea of functional response. What is functional response? Is pretty easy. Suppose you plot on the horizontal scale the prey density, how many preys are in a given area, and then you measure predation rate, how many preys are eaten. And the function that is predation rate as a function of prey density. For example, here the function is linear, but you can think of anything. I mean, you can change the function. Of course, it's reasonable that the functional response is increasing, or non-decreasing at least, weakly increasing, and what else? Well, Holling came up with classification, 3 types of functional response, reasonable functional responses. Type 1 is linear response. One example, biological example of a linear functional response is again for the lemmings. But now we measure how much the lemming eats as a function of the biomass of the food. The food is, and you can see that pretty much is linear. I mean, it doesn't go through the origin. There is a reason for this, but I can't remember it now. So this is type 1 functional response. Type 2 functional response is something like this. Starts slow, then it goes up quickly, and then it reaches saturation. This is an example. Predation by wolves upon caribous in, again, Alaska, I think, or somewhere. And you can see, well, it's not very clear, but something like this. Up quickly and then saturation. This is type 2 functional response. Type 3 functional response is more complicated. It goes up slowly at the beginning. It takes up speed and then saturation. This for type 3. I won't talk about type 3 again. Then Harding came up with a so-called disk equation. He invented an experiment where there is a table. Actually, he made an experiment, a table. He put some small disks on the table at random, like this. Then he blindfolded an assistant, and the assistant had to find the disks by tapping random on the table. When the assistant found a disk, she had to take the disk and put it into a box, then start again. In a given time, they counted the number of disks taken as a function of the density of the disks. This is the result of the experiment. Is a type 2 functional response. And Harding came up also with a theoretical equation, something like this. This is called a disk equation, where P is disk density, I mean the Prey density. You can see Prey density is, as a function of a Prey density, it is a rational function of the first degree. So, and this is the fit, I mean the best fit for the experimental data for this equation. Okay. So, what if we put a functional response into classical Lotka-Volterra? So, this is classical Lotka-Volterra. So, let us, classical Lotka-Volterra is type 1 functional response, linear in Y and linear in X. So, this is Lotka-Volterra with functional response Fy g of x. For example, we can choose a disk equation. This is a functional response of the disk equation. What happens to the system? For example, for this system here, well, it's pretty easy. Well, the picture is pretty much the same. Well, this is actually, it is the same. It's type 1. For type 2, it's a little different, but only slightly different. You can see here, these lines are not convex. They are a little concave. But for the rest, it's very similar. I mean, the qualitative dynamic is the same. So, Harding's model is very sophisticated with respect to time. It takes into account how much time it takes to find the prey, then the metabolic, digestion time, then the learning time. So, it's very sophisticated with respect to time, but not sophisticated at all with respect to space. Actually, space is only taken into account as through the density of the population, the density of the prey. Is the only parameter. So, as far as space is concerned, it's very rudimentary. So, here we come. Our simulation model, it takes into account space only. And see what happens. So, oof. So as the distribute population, mixed population, predators and prey on a square, and at random, we want them to interact. How? To interact in a spatial way, through space. For example, here we have a couple, predator and prey, which are very close, so there is a high probability of interaction. This is a predator which is very far from prey, so we suppose that it has a little probability of interaction. This is the big idea. Make the probability of interaction depend on the distance. In particular, we make every predator, for example, interact with the nearest prey only. Why? Because it's simpler to calculate. So, for each predator, we find the closest prey, the closest, nearest one, and we make the interaction depend on the distance. And the same way, for each prey, we find the closest predator, and we make the interaction depend on the distance. Now we must quantify the probability of interaction. How? The easiest way that we found, the most reasonable, is to make the interaction depend on 1 over r squared, where r is the distance. Why? This interaction law is because the quantity of light that comes from the predator, from the prey, to the predator I, goes as 1 over r squared. At least if there are no impediments, if there are no other dispersion. So if the prey is very close, a lot of light will come to the predator. If the prey is very far, much less light will come. And arbitrarily, we link the probability of interaction with the distance through this function. So this function is here, 1 over r squared. Of course, there is a problem here because 1 over r squared goes to infinity. Probability cannot be infinity. It can be less than 1. So we make a cutoff. For example, we make a cutoff at level 0.4, for example. If a prey is very close, it doesn't matter if it's 1 meter or half a meter, 1/3 of a meter. Doesn't matter, shouldn't matter much. So I suppose that cutting off is not very, it's pretty reasonable. One can think of a different interaction laws. For example, if the light is attenuated, for example, in murky water, or if there are foliage around, only a little light can come. So we take that into account by multiplying with an exponential decay with r. This is also a reasonable, we think it is a reasonable interaction law. This one too goes to infinity, so we cut it off at level 0.4, for example. Another possible interaction law is by gradient of smell. Some animals can smell the prey, but smelling alone is not enough because we can tell, for example, there is a prey, maybe also distance, but where it is. To find the direction, we need the gradient of smell. We have to smell around and find where the smell is stronger and go in that direction. So the gradient of the smell is 1 over r square, r cube, I mean. We cut it off again. One more possible interaction is by sonar, 1 over r4. I mean, for example, the bat emits a sonar impulse that goes, it meets some butterfly and goes back. The attenuation is 1 over r cube, r fourth, I mean. Maybe also luminescent fish in deep sea do something like this, perhaps, I don't know. Anyway, we do the same here. So,
this I don't understand. Why 1 over r4?
Because there is one alternation going that way, then one more alternation going back. So, summary of interaction laws. Anyway, sorry. This is 1 over r square with exponential attenuation, 1 over r square and 1 over 4. 1 over r to the power 4. We only used these interaction laws, but you can put any interaction law that you can think of into our again. So here, for example, take this point. The nearest predator is here. Here you have the radius, I mean a distance from the center here, and the probability of interaction with this interaction law. If you change interaction law, of course, the radius is the same, but the probability is different. You can change the interaction law. There is a complication because if we are not careful, I mean, predators or prey which are close to the edge have an advantage or disadvantage. I mean, it's not homogeneous space, so we wrap the square around into a torus. So, for example, this position feels the presence of those predators which are on the other side, and so on. So you may think of the population as living on a torus. So, population of living on the surface of a torus. So, our model specification. For the prey, probability of dying is the minimum of h of r. H of r is the interaction law, cut off by c. Then the probability of reproduction is constant, and then probability of doing nothing is what is left, complement to 1. For the predator, probability of dying is fixed. Probability of reproduction is interaction law, cut off by c. And the probability of status quo is complement to 1. So at every step, the position of the individuals are shuffled around randomly. So connection between the position of a predator at some time with a position at a later time, independent positions. So I'll run the simulation and see what happens. So in real time, the predators are red, preys are blue. To the left is time versus the population. To the right there is preys and predators. Oh, I wrote in Italian. So you can see there are oscillations. I mean, not exactly periodical, but, well, not too bad. Well, this is a simulation. I could change the parameters or the interaction law, but I don't have much time. So, I mean, we could be content with this for now. Next step was to develop some theory, microscopic theory of this stochastic system, and to find a deterministic system that reproduces these oscillations. I mean, in a quantitative way. Is it possible? So, well, some impression on the simulation result is that we have oscillations, and pretty much regular. I mean, they're not too bad. They go around in the right, in the phase space, so they go counterclockwise. They're not exactly periodic, but often they come to an extinction, pretty often. So, but more or less they are similar to the Lotka-Volterra dynamic. So, we want to find the functional response of our model. What is the functional response for this stochastic model? We came up with an answer. So, again, just why this? So we made a statistical analysis of our model. For example, take the center of the square. Take a population of predators, for example. Here, the nearest one is at this radius. Try again a different population of the same size, but random. Here you have a different radius. Go try again, try again. We make a statistic of the radius r. And this is the empirical distribution of r. For this number of predators, for 20 predators, and the sample size of 100, if we go up the sample size, you can see some statistical distribution appearing. You can change the predator's population. So, this is empirical. Can one find an analytic function, formula that gives this distribution? Well, yes. Well, not exactly, but we came up with this formula here that it's pretty close. I mean, it involves some approximation, but this is a theoretical distribution, depending on the number of predators. And let us compare it with an empirical. Well, not so bad. Let us change the predator number. Well, we make this empirical check because our reasoning is not entirely rigorous. So, I think it is not too bad. So, this is the chart of the theoretical distribution of the probability of interaction versus the empirical distribution, but I will skip this. Now we go to the mean probability of interaction, which is a main point here. The mean probability of interaction, we can find a formula for this, integral formula. I skip this. And here is well, anyway, forget about this global and global because I don't know why it came. It's the first time I see this. I worked a few days on this, and the first time I get this global. Anyway, let's chart here. This is the functional response for 1 over r to the 4th. This is the functional response. If we go to the 1 over r squared, this is the functional response. 1 over r cube. You can see it is a type 2 functional response in all cases. And we also get a formula, I mean an analytic formula for the functional response. It involves, you see, pi. This is a hypergeometric function. There is a gamma function here, and maybe something, one more gamma. This is for 1 over r cube. For 1 over r squared, it contains this price with polygamma. Gamma is Euler constant, I think, and hypergeometric function here. So this functional response contains special functions. But with this program, we don't care about special functions. They work. So this is our the specification for our stochastic model. So Lotka-Volterra equation with functional response. We choose as functional response the functional response we found in the previous slides. I don't know, it's terrible. Well, anyway. So this is the phase plot for interaction 1 over r squared. You can see it's very similar to, I mean, qualitatively the same as Lotka-Volterra classical. For 1 over r cube, it's pretty much the same, but you know, the equilibrium point is very different. Here, the equilibrium is, wait a minute, doesn't respond. Yes, 4,000, around 4,000. For 1 over r cube, it is much less, 200. For 1 over r fourth, it is even lower. It's 40, the equilibrium point. So qualitatively it's the same, but quantitatively it's very different. So let us compare stochastic versus deterministic model to see if they agree. So I choose initial point of 3,300, which is around here, in this place here, and see if our trajectory follows the theoretical lines, I mean the deterministic lines, and see what happens. I hope it works. Well, it doesn't work. No, wait a minute. Yeah, it works. Very slow. Okay. At 2 o'clock it worked. It worked. Sorry, the last one. It's stuck. Start again. Non lo so, a volte mi fa questo scherzo. I have to recompute all the integrals, which takes some time. Ah, yeah, no, it's better. So here's the time here and populations on the vertical. Here you can follow the populations in the phase space. Well, here I started very close to the equilibrium, so it's pretty random over there. Well, it's reasonably close to the deterministic equation. So, well, this is it. I'm sorry for the last simulation.
Can you mention again what are the differential equations for the right phase space? It's what you call the deterministic model.
Yes.
With
So.
With the F you determine.
This is the equation f and g. Here it is. F1 or equal g1 is equal to this function here. Yeah. For the 1 over r to the fourth. For example, for 1 over r square, it's this one. This is a hypergeometric function, polygamma, and so on. These are the equations. They come from statistical reasoning. Yes. Yes. Independently, yes. And this is not very reasonable, but otherwise we cannot do anything.
The eating is taking place in a time scale much smaller than the distribution of the species are moving much faster than they eat.
Yes, each time they are just shuffled around at random. Then they eat again, depending on the distance. Then the next day they are shuffled around again, and so on.
I guess the computational work for doing it you thought the distributing is going to be huge, right?
What?
The computational work to do it without redistributing the population, keep track of everything all the time.
Well, no, it's not. So you can see that it goes pretty fast.
No. Without the distributing. Without the shuffling.
Without the shuffling, yes. The first time we tried was by moving around as a Brownian motion. But then it didn't work because we found that there were islands of predators, islands of prey. They collapsed and didn't follow a nice oscillating cycle. So we wanted to find a statistical model that followed more or less Lotka-Volterra. And well, this one works. I don't know how reasonable it is in practice, but it's a toy model. A toy model that works.
How about experiments after biological experiments? These models that you are proposing mathematically?
Actually, we heard about an experiment and Luckinbill experiment, putting two species of bacteria into a somewhere into a box in the water, and one of the species attacks the other, so it predates on the other, and if they put them into water, I mean, one of the two species dies off very quickly. But they discovered that if they add some gel or something that makes, moving slower, they could make some oscillations appear. I think maybe this model could model, 3-dimension. I don't know how the bacteria interact, but maybe by smell. Well, not by sight. Maybe by smell. So maybe we could try to make a model, a spatial model, and try to fit the data. Maybe we do not try.